Welcome back to Mind Maths. In today's macroeconomic lesson, we're going to examine how a government spending shock works inside the three equation new Keynesian DSGE model. We look at how the shock moves through the IS curve, the Phillips curve, and the monetary policy rule, and how these interactions shape output, inflation, and interest rate over time. The goal is to understand not just the direction of the effects, but also the dynamic adjustment path of the economy. And it is also actually solved quite similar to the way we solve for a monetary innovation shock. So let's begin. We are given these three equations: the IS curve, the Phillips curve, and the Taylor rule curve. And for simplicity, I'm going to assume that there is no growth in technology and there's no shock in inflation or output, and also that the coefficient of government spending in the Phillips curve is equals to 0. I'm doing this for simplicity, so to ensure that we have a model which is easy to solve. Okay, since there's a shock in the government spending, I'll have to make that into an AR1 process. Okay, so the shock is variable is government spending, so I have to turn it into an AR1 process. And so GT would be equals to rho GT minus 1 plus a white noise epsilon, where the value of rho is between 0 and 1 depending on how impactful the shock is, if it's permanent or if it's temporary. Okay. Remember, just like in the previous case, I substituted the Taylor rule into the IS equation so that we have a 2 by 2 system. We're going to do the same thing again, but let's first start off by putting in all of these assumptions that I made to make our model more simple. So let's do that first. Shift this here, shift this here, put these equations here. Okay, so we assumed A is equals to 0, so this goes away. There's no inflation shock, this goes away. The coefficient of GT is 0, so this goes away. There's no monetary innovation shock this time. There's no output shock, and that's it. I think this is all the simplifications that we made. Yeah, that's it. Okay, and what we're going to do, we're going to substitute the Taylor rule into the IS curve to get a 2 by 2 system, because that's going to be easier to solve. So let's do that as well and then continue. So this is my IS curve, and I have to replace the interest rate here with the Taylor rule. So we have a central bank that does output and inflation targeting by adjusting the interest rate. So we don't have a central bank which pursues monetary targets. We have a central bank which has inflation output targets. Okay, so this is my equation 1. And my equation 2 is simply the Phillips curve. Okay, I think I did copy it, paste it down here. Okay, this is equation 2. Okay, so I said at this point, the first most important thing is to identify the endogenous variables. And you can see that the endogenous variables are YT and inflation T. And one tip is that whenever we make the aggregate demand curve and the aggregate supply curve, we have output and inflation on the axis. So this is how we understand that these are variables determined within the model, so they are going to be endogenous, and whatever other variable depends on these as a consequence will also be endogenous. So if I say consumption depends on output, where output is endogenous, so that will make consumption endogenous as well. Okay, moving on. Exogenous. Actually, in this model, we don't need to state the exogenous variables, although they are going to be, we don't have any past values, so we don't have any exogenous variables besides the shock itself. And these are parameters. We don't need to mention all of this. We're not running a model in MATLAB. So, okay. The next thing that I need to state is the shock. The shock is basically on government spending, which we just claimed to follow an AR1 process. Okay. Next is to state the trial solutions. So we can see what the multipliers become. Okay, we can say YT is equals to AGT, which in this case, A is going to be the government spending multiplier, because that is exactly the derivative of Y with respect to G. Okay. And another thing that we can see is that the expected value of t plus 1 at this period's time is just going to be constant A, and expected value of t plus 1. And we know that over here we can actually write this fact over here, that if I take the expected value at time t of gt plus 1, it's going to be equals to rho expected value of gt, and the expected value of et is simply a 0, because it's white noise, right? So it's normally distributed with mean 0 and variance 1. So this becomes rho gt plus a 0. So I'm just going to substitute this here. Instead of deriving it here, I'll just write that the value of this is rho gt. Okay. Okay, the next trial solution is for the next endogenous variable, which was inflation, and we can call the multiplier here C, and the value of C is the change in inflation because of a change in government spending, and there's what is the expected value of future inflation. It's just going to be C rho gt. It has the same derivation like we did for YT plus 1. Should I write this down for you guys or not? Maybe I should. I don't know, but I actually have explained it here, so I don't think I need to write it down again. Anyhow, so now that we have the trial solutions, you have to put the trial solution into equation 1 and 2. Very similar to what we did in differential and difference equations, where we put a trial solution into the equation. So let's do it for this first. Okay. Actually, I'm solving this for the first time, so I'm a bit anxious about getting it right. Okay, so I have a GT and a rho GT minus gamma uh, sigma minus 1 coefficient of output into, there's going to be a GT here, coefficient of inflation C GT minus C rho GT. Okay, phew. And actually, I solved this question once before last year with my students, but I had very conveniently taken the value of gamma is equals to 1, so all of this expression wasn't there, and this became a 1 over. So um, I I think we should not have made that assumption. So in this class, I'm actually not assuming that gamma is equals to a 1. So I'm not going to assume that for simplicity here. Okay, and then we have a GT minus um, expected value of GT plus 1. What is that going to be? We can see it from here. So GT plus 1 is rho GT plus expected value GT plus 1. So the expected value of GT plus 1 is just rho GT. Okay. So minus rho GT, and yeah. Okay. So as you can see, GT actually can be taken out as common, and it does cancel out everywhere. If it doesn't, then that's just a hint that you've done something wrong. So you have A is equals to A rho minus gamma inverse of sigma coefficient of output, okay, into A. And then we have a minus gamma inverse of sigma inflation coefficient C minus rho C. Yeah, because no, there's a minus there. This is going to become a plus then. Yeah. And then plus 1 minus gamma 1 minus rho. Okay, so let's take A and C over to the other side. So I'm going to get a 1 minus A, 1 minus rho plus gamma inverse of sigma coefficient of output, and all of this is with A. I'll just highlight this for you. Yeah. Okay, what about C? So with C, I'll have a gamma inverse of sigma coefficient of inflation, and then a minus rho into a C. And wow, there we have it. I hope to God this is the correct solution, otherwise it's going to be really embarrassing. But even if it's not the right solution, the method is still correct. And if I made a mistake, it's just a mechanical mistake, not something that you could get penalized for. At least I wouldn't do any negative marking for a silly plus minus error. Okay, the second equation is this, and we want to now substitute the trial solutions here as well. This is actually shorter, so it should be easier to manage. This weird x c rho gt plus whatever the symbol is a gt. Again, the gt is very nicely eliminated, and then we can make a the subject. So a comes here, plus 1 minus x rho c is equals to, okay, we have a 0 here. So this is the equation 2. So now we want to convert it into a 2 by 2 system, and then we want to find the value of the multipliers. Let's go ahead with this. Okay. So converting into a matrix form is actually the easiest part. I think in my last lecture when I solved this, I took the inverse of this matrix, but if we want this time, I can actually use the Cramer's law, the rule, because I find Cramer's rule the easiest. 1 minus xb. Okay, and over here I have a 1 minus gamma, 1 minus rho, and a 0. Okay, so let's use the Cramer's rule this time, because in the previous lesson I actually just took the inverse of this matrix and I multiplied it with this column vector. So let's instead just do the Cramer's rule. Okay, the determinant of this matrix is 1 minus rho plus gamma inverse of sigma coefficient of output multiplied by 1 minus x rho plus this expression and this expression. So that's the determinant, and I believe this is actually, it looks greater than 0 because this is a fraction multiplied by fraction is a fraction, so this is positive, and all of these are also very small numbers, so I think the determinant is actually greater than 0, but maybe it's not, let's see later. Okay, so this is the determinant. So the value of a is the determinant of the matrix this. If I replace the first column with the column vector b, usually known as b. Okay, so this is going to be my answer for A. And what am I expecting the answer to be actually? I'm expecting that a government spending shock would shift the IS to the right, and therefore I expect the AD to shift to the right. So I'm actually expecting output to rise and inflation to rise. So therefore I want a value of A greater than 0 and C greater than 0. And if it's anything besides that, then I will know I've made some kind of error. So let's put the determinant here. Okay. So this is the this one goes here and multiplied by this. This is actually greater than 0 as expected, because we know the value of I can actually say this is greater because or if and only if gamma is less than 1, rho is less than 1, x multiplied by rho is less than 1. So and basically these things are true. So moving on to find the value of C. C is going to be the determinant of the matrix. If I replace the second column with B, so let's do that. I'm going to replace now the second column with B. This is the column vector usually known as B, because we actually usually write this system as AX is equals to B. So that's why I'm calling it B. Okay. And I'm going to divide this by the determinant. Okay, and this becomes a positive, this 1 minus gamma, 1 minus rho over the determinant. And this is going to be positive as long as gamma, I don't know what this thing is called, the symbol is greater than 0, which it is actually. So yeah, we have proven that a rise in government spending, which shifts IS to the right, and therefore it's a demand shock to the right, will lead to a rise in output and a rise in inflation. And what about interest rate? The third equation can actually tell us what happens to the interest rate, but we can actually also make sense of what happens to the interest rate diagrammatically. Okay, let's see how the interest rate changes after shock in government spending. This is going to be the derivative of y with respect to g, coefficient of inflation, derivative of inflation with respect to g, and this we've calculated before as being a, and this is a c, and therefore these are actually, this is greater than 0. So it kind of shows that the interest rate rises, so there is some kind of crowding out by investment. By investment. So I think how the visualization we can give ourselves is that if this is the IS curve and this is the LM curve, if the IS curve shifts to the right, we move from point A to point B and then to point C, where this rise in the interest rate is the crowding out. So the interest rate overall is rising, and we can use the ADS model to see the impact a rise in government spending would have on the output and inflation levels. The AS and LM curve are captured by the aggregate demand curve, whereas the short-run Phillips curve or the short-run supply curve is positively sloped. So basically, if we start off at point A, a rise in government spending would shift AD to the right, and therefore we will end up in a place where there is a rise in output and inflation, at least in the short run. So yeah, that is the ending of this actually. So as a conclusion, this completes the dynamic analysis of I love putting this line here. Anyhow, this completes the dynamic analysis of a government spending shock in the new Keynesian 3 equation model. We saw how fiscal policy influences output and inflation, and how monetary policy responds to the interest rate rule. Um, and I'll Yeah, that's it. This was just the standard government spending shock in a DSGE model, and I'll see you in the next part. Take care for now.